Good evening. In this video, we are going to talk about Proposition 9 from Book 2, which is pretty interesting. So it declares that if we are given a finite string line AB and a point C that evenly divide AB into two equal segments, and another point D that unevenly divide AB into two unequal segments, AD and DB, then we will have that the squares on the two unequal segments, which means the square AD and the square BD, together they are equal to twice the square on the half. C evenly divide AB into two equal segments, so the half will be AC square, as well as the square on the straight line between the evenly divided point and the unevenly divided point, which means CD. Okay, CD square. So let's give it a proof. So first of all, please recall proposition 11. So we are able to construct a straight line that is perpendicular to a given straight line through a point on this given straight line. So let us construct this straight line that is perpendicular to AB, and then let us apply proposition 3 from book 1 to cut off CE here, such that CE is equal to AC and BC, okay? And then apply postulate 1 to join AE and BE respectively. Okay. So based on this construction, currently we know that CE is perpendicular to AB and CE is equal to AC, and since AC is equal to BC, so it is also equal to BC because of common notion 1, okay? And then let us construct a straight line applying proposition 31, okay? So this time we construct a straight line through the point of D that is parallel to CE. Sorry. And let's assume this straight line meets BE as a point of F. So we know that DF is parallel to CE. And then let's apply this proposition again to construct a straight line here that is parallel to AB, okay? And let's assume this straight line meets CE as a point of G. So we have FG is parallel to AB, correct? And then let's apply postulate 1 again to join two different points A and F together. Okay. Okay. And let's start the proof, okay? So first of all, please recall proposition 32 from book 1. The two opposite interior angles, the sum of them is equal to the opposite exterior angle. So have a look at this triangle ACE. Let's mark them as angle 1, angle 2, angle 3, and angle 4. So we know that angle 1 plus angle 2 is equal to a right angle, right? This is the exterior angle, and these are two opposite interior angles. So similarly, we have angle 3 plus angle 4 is also equal to a right angle. Okay, this is the exterior angle, and they are two interior opposite angles, correct? Okay, and we know that CE is equal to AC is equal to BC, correct? And if we apply proposition 5 from book 1, we know that in an isosceles triangles, those two angles are equal on the base, correct? So since AC is equal to CE, we know that angle 1 equals angle 2, correct? And CB equals to CE. CB equals to CE. We can conclude that angle 3 is equal to angle 4. They are based on proposition 5, okay? And if we combine these two equalities, we can conclude that angle 1 is equal to angle 2 equal to angle 3 equal to angle 4 equals to half of a right angle, correct? Okay, let's keep this conclusion here. Great. And in the next step, let's think about proposition 29 from book 1. It declares that if a straight line is falling on parallel lines, then the exterior angle is equal to the opposite interior angle, okay? So have a look at these two pairs of parallel lines. We know that DF is parallel to CE, correct? DF parallel to CE, which means, let me check. This angle must be equal to this angle, correct? Let's mark it angle 5. So we have angle 3 is equal to angle 5 because of proposition 29, correct? And we also know that GF is parallel to AB, correct? And apply this proposition again, we can conclude that, let's make it angle 6. Angle 6 is equal to angle 4, correct? Because this straight line is falling on these two parallel lines. So this is the exterior angle and this is the opposite interior angle. Just recall this proposition, correct? And let's keep these two conclusions here again. Okay, so angle 3 equals to angle 5 and 6 equals 4. And if we combine these two conclusions together, we can imply that angle 3 equals to angle 6 and angle 4 equals to angle 5, correct? And let's apply proposition 6 again. Proposition 6 is it states that if two angles are equal in a triangle, then the sides subtending them are equal. So it is pretty similar to proposition 5, just reverse it, okay? So we know that these two angles are equal. So in this small triangle, we can conclude that GE will be equal to GF, correct? And in this triangle, we apply proposition 6, we can conclude DF will be equal to DB, correct? Okay, let's put these conclusions here again. And in the next step, let us apply proposition 47. It is Pythagorean theorem. So in the triangle ACE, it is right angle triangle. We can conclude that AC square plus CE square is equal to AE square, correct? And since AC, where it is? Okay, AC is equal to CE, so we know that AE square is equal to twice of AC square, correct? Okay. And let me check. Okay, this is a right angle, correct? Because they are perpendicular to each other. And if we apply proposition 29 again, we know this is another right angle because they are parallel. This is the exterior angle and this is the opposite interior. So triangle EGF is also a right angle triangle. So let us just apply Pythagorean theorem again. We have GF square plus GE square will be equal to EF square. And we already know that GF is equal to G, so it is EF square is equal to twice of GF square, correct? And if we recall proposition 34, we know that the opposite sides of a parallelogram are equal. So CEFG is a parallelogram because we construct it like that. They are parallel, so it's a parallelogram. So we know that FG is equal to CD, correct? And if we combine FG equals to CD together, we can conclude that EF square will be equal to twice of CD square, correct? Okay, and let's have a look at this triangle again. We apply proposition 29 again. They are parallel, so this is a right angle, so this must be another right angle. So FDB is also a right angled triangle. So let's apply Pythagorean theorem again. We conclude that DF square plus DB square will be equal to FB square. Okay, and we have known that angle 2 and angle 3, both of them are equal to half of the right angle. So this angle is also a right angle because it equals to angle 2 plus angle 3. So this is another right angle triangle. So if we apply proposition 47 again, we know that AE square plus EF square will be equal to, let me check, AF square. Oh, I'm sorry, this is not necessary. Okay, AF square. Great. And if we apply this theorem again in this triangle ADF, okay, what we have that AD square plus DF square will be equal to AF square, correct? And if we combine these two equalities together and apply common notion 1, we know that right sides are equal, so left sides must be also equal. So AE square plus EF square will be equal to AD square plus DF square, correct? And let's just plug in AE and EF from the previous conclusions. So what is AE squared? We have proved AE squared is equal to twice AC squared, correct? So it is, sorry, or let me write it here. So we know that AD square plus DF square will be equal to, let's plug in twice of AC squared here, twice AC squared, and EF squared. We know that EF squared is equal to twice of the CD square. Okay, let's plug it in here. So plus twice CD square. Okay, so we have this conclusion, and in this triangle we know that angle 4 is equal to angle 5, and if we apply proposition 6, which is the converse proposition of 5, we know that these two sides must be equal. So FD is equal to BD, and let us replace DF with BD. So we know that AD square plus BD square will be equal to twice of AC square plus CD square. Okay, and this is a proposition we are trying to prove. See, they are equivalent. So I think this is the end of the proof. Okay, and to be honest, this is a proposition that Euclid started to abandon, demonstrating them with rectangles and and squares. But to be honest, we are also allowed to prove this proposition by constructing squares and rectangles on this finite straight line, very similar to proposition 1 to 8 from book 2. Okay, we'll just skip that proof. And this is the end of this video. Is next one we are going to discuss proposition 10 from book 2. Thanks for watching. Have a good day.